we are looking at section 8.1, and we have a couple review questions here before we start on the new stuff. And we have some similar triangles, and we're supposed to find x and y. So I'm going to say x is to 11.7 because those are the longest sides both. And if we look at the shortest side, 2.8 is to 4.2. Now I'm pretty sure you guys can all solve that, so I'm not going to. But I am going to set up the one for y. And again, I'm going to use the 2.8 to 4.2 because that's the one side that's given in both that correspond to each other. And I'm going to use the 5.6 is to the y. And if you want to, you can solve those. In the second warm-up question, we're given that we have two similar triangles, and we know that the perimeter of the first one is 26.5, and we know that if we look at the similarity statement, that AB and DE are the two that are proportional to each other. So I'm going to set up my proportion. AB is to DE as the perimeter of ABC is to the perimeter of the other one. And again, pretty sure you can solve that. The thing that you need to remember here is the side ratio and the perimeter ratio are the same ratio. We have the quadrilateral has a perimeter of 56 units after the dilation with a scale factor of 2. What will the perimeter of so the original has a perimeter of 56 and our scale factor of 2, which means it's an enlargement by a scale factor of 2. So since the scale factor is 2, that means it's going to be twice as long as the original. So if I do the cross products here, I end up with 112 units. Alright, so what we're going to be learning today is we're going to be talking about geometric mean, and in the past you've done the arithmetic mean, which is adding two numbers together and then dividing by 2. Well, the geometric mean is multiplying them together and then square rooting. So the geometric mean, we're going to take a times b and then square root. And that'll give us what the geometric mean of those two numbers are. And we're going to solve some problems, a lot of finding parts of right triangles with altitudes in them. And we have a whole bunch of theorems that go along with that. So again, our geometric mean, instead of adding together and dividing by 2, we multiply together and square root. And where does that come from? Well, in this triangle down here, we know that the geometric mean, because we have two similar triangles, it's actually 3, but we're going to say this triangle is similar to this triangle. And those are the two that I need for this. And if we look at it, the long leg, I'm going to call this long leg, and I'm going to call this short leg of the bigger of the two triangles. And in the smaller triangle, this is the long leg of the smaller triangle, and this is the short leg. So the way we set this up is that A is to X as X is to B, and when we do our cross products, we get A times B square rooted, and that's going to help us find that X value. So that A times B square rooted is going to give us our geometric mean. And so if I'm just given two numbers to find the geometric mean, I take 3 times 12 square rooted, I get 36 square rooted is 6. So in this first theorem, it's telling me if I draw an altitude in any right triangle, that it's going to cut it into three, count them, 3 similar triangles. So we have the smallest one, we have the middle-sized one, and we have the one that is the biggest one. So those are the three triangles that they're talking about when they say that it's going to cut them into similar triangles. Take some time to write that down. You're going to want it. So in this one, they're saying, hey, can we write the similarity statement for these? And again, I'm just going to make sure you see the three triangles. And we can see that if we take this red one, if I can grab it separately, I'm hoping I can, and I rotate it and slide it, I don't want to slide the whole thing, I just want to slide you. Slide it over here next to the black one, you see that it's a similar triangle as that one. Then if I take it again and rotate it and flip it, so I got to rotate it and flip it, that's going to be it. Let's see if I can do this. I don't know, sometimes I can, sometimes I can't with these rotations. But with this, I get the same as the green one, similar to that one. So that's how we get the three triangles. Okay? And the names of them I think I have on my next screen, so there they are. Triangle EGF is similar to triangle FGH is similar to triangle EFG. And if you haven't tried this, you should definitely try to name the similar. That's been a question on tests, my tests about this section for years, is take the original triangle and say the similarity that you have with the three triangles. Okay. So we have the geometric mean, which is the altitude. So we know that x is to h as h is to y. But we also have the geometric mean in the legs. So let's take a look at over here. We know that x is to b as b is to x plus y, or I think they called it c here instead of x plus y. And the same is true of a side A. We would say y is to a as a is to c. All of those are ways to set up your proportions to find not only the altitude, but these two legs. And there are proportions to do both of those. Okay? All right. And we'll be doing problem. Hey, let's just do this one. So, if I want to find E, of course, I would say 6 is to E as E is to 24 and get the geometric mean of that. Then if I wanted to find C, I would say the part of the base that's next to the side that we're finding, in this case C, is to C is to the whole side, which is 30. Now let's take a look on where does this come from. We're taking parts of this triangle, which is the second largest one, and we're comparing them to parts of the whole triangle, so the biggest triangle. And what we're comparing here on the red one here is this is the long leg, and part C is the hypotenuse. So on the red one, I'm going to say 24 is to C. Now if we look at the green one, the C is now the long leg, and the 30 is the hypotenuse. So that's why the two triangles that we're comparing. Now let's find one more. Let's find D. And I'm going to say 6 is to D as D is to 30. Now, on this one, we're comparing the small triangle and the large triangle. So let's see if we can compare. This is the short leg. So we're comparing short legs and the hypotenuse. Short leg is to hypotenuse. So black short leg is to D, the hypotenuse. as in the bigger one, the green one, this is the short leg, and these two together are the hypotenuse. So that's how we set up to find those parts in a triangle. All right, so if I'm going to find these, I'm going to set up 4 is to F as F is to 20. Again, the part that's next to the side that we're finding is proportional to the side that we're finding to the total. So if I'm going to find E, I'm going to say that the part that's on the E side is to E as E is to 20, the whole thing. So that's how you would find that. Now don't forget about our friend Pythagoras. If we know that this part is 16 and this part is 8, we can find that E using the Pythagorean theorem also. But since we're in the section with using the proportions, I thought I would set them up that way. So here we got an application question, and we're going to try to find the length. The airplane jetliner has a wingspan dB of 211 feet. The segment drawn from the front of the plane to the tail at point E, so it's interrupt. If AE, this part here, is 163, what is the length of the aircraft to the nearest tenth of a foot? So we have this length here. If we know the whole thing is 211, then this part is 105.5, and we can use our proportion. We can say 163 is to 105.5 as 105.5 is to x. And I'm going to actually find this answer because that's a good one to find. 105.5 times 105.5. And I'm going to divide that by 163. And I get that this x portion of it is 68.3 feet. But that's not what it's asking. It's asking for the whole thing. So I'm going to add 163 to that number. And so the whole airplane is 231.3 feet long. And that is it for this section.